How is a nuclear explosion built? I think many viewers of my channel have at least some idea about it, and at the very least, they know that a nuclear explosion is a very rapid release of energy sealed inside the nuclei of atoms of radioactive elements, usually uranium or plutonium. But how exactly is this energy released? In what specific forms does it appear? And how does it transform into the destructive factors of a nuclear explosion, such as the blast wave, light radiation, and so on? That is exactly what we're going to talk about in today's video. We will examine how a nuclear explosion actually occurs, what processes happen in its core, and in what sequence, and how all of this affects those unlucky enough to be nearby. At the core of a nuclear explosion lies the process of induced fission of atomic nuclei of certain radioactive isotopes, such as uranium-235 or plutonium-239. These nuclei have an interesting property. After absorbing a neutron, they enter an excited state and split into two fragment nuclei of smaller mass, releasing a few more neutrons in the process. Each of those neutrons, in theory, can also initiate a similar act of fission in other atomic nuclei, which will in turn release even more neutrons. Those neutrons can trigger the fission of still more nuclei, releasing still more neutrons, and so on. Such reactions, in which the process itself produces what is needed to sustain it, are called chain reactions in both chemistry and physics. The total mass, and therefore the total energy of the fragments, turns out to be smaller than the energy of the original nucleus. It is precisely this missing mass energy that is released during induced nuclear fission. And since, within a very short time, a very large number of nuclei split per unit of time, an enormous amount of energy is released per unit of time. That is what we call a nuclear explosion. However, energy is not some independent substance. It is merely a characteristic of physical objects, a measure of their ability to perform work. Therefore, whenever we speak about the release of energy, we must understand which objects receive this energy and in what form. In the case of a nuclear explosion, the energy is released in three main forms. First, it appears as the kinetic energy of the very neutrons emitted during the fission process. This accounts for about 3 to 4% of the total energy of the nuclear explosion. Part of the energy transforms into excitation energy of atomic nuclei, whose nucleons move to higher energy levels. Ultimately, this is also kinetic energy, but of nucleons that remain bound within nuclei. After a short time, this energy is emitted as photons with energies of about 4 to 6 mega-electron volts. This is hard gamma radiation, the so-called penetrating radiation, and it makes up about 5 to 6% of all the energy released in the explosion. Third, a significant part of the energy goes into the kinetic energy of the fragment nuclei flying apart in different directions. As we remember from school physics, the kinetic energy of atoms or molecules is nothing other than the temperature of matter, up to a constant known as the Boltzmann constant. Thus, in effect, this portion of energy is spent on heating the material of the bomb itself and the surrounding air. About 90% of the total released energy is spent on this heating process. Well, now let us see what happens next with all that released energy. The streams of high-energy neutrons emerging from the center of the explosion are themselves a destructive factor. They are especially damaging to living organisms, causing complex combined disturbances in their biochemistry. One distinctive feature of neutron irradiation is that neutrons can become embedded in atomic nuclei, which then turn into radioactive isotopes of the same chemical elements. For example, sodium-23, which is present in the tissues of the human body, can absorb a neutron and become radioactive sodium-24. In other words, after exposure to an intense neutron flux, the tissues of our body themselves become radioactive, a phenomenon known as secondary radiation. Of course, neutron streams create secondary radiation sources not only in living tissue, but in all materials in general. For instance, when a neutron collides with stable iron-56, it can knock out one of the protons and take its place, transforming iron-56 into highly radioactive manganese-56. The half-life of manganese-56 is about 2.5 hours, so within a day or two it completely decays. But during that time, it can do serious harm to anyone who happens to be near metal objects that have been exposed to neutron radiation. That is why the neutron radiation of a nuclear bomb is considered a kind of selective destructive factor. It acts mainly on living beings close to the explosion's center, while having relatively little effect on inanimate objects. This very property gave rise to the concept of the neutron bomb, a weapon designed so that the share of energy carried by the neutron flux increases to about 30 to 40%. The idea was that all enemy personnel would die, while buildings, structures, and machinery would be only lightly damaged. Neutron bombs are a type of thermonuclear rather than purely nuclear weapon, so the physics of their operation goes beyond the scope of our discussion. Still, it would be impossible not to mention this technology here. In conventional nuclear bombs, the neutron flux is also a powerful destructive factor, but its range is limited. Even when traveling through ordinary air, let alone through denser materials such as building walls, it weakens to nearly safe levels at a distance of only about 2 to 3 kilometers from the explosion's center. People within that range would indeed receive lethal radiation doses, but radiation would hardly be their main concern. For the vast majority of modern nuclear weapons, they would die much more quickly from other destructive effects of the explosion, which at that distance are unimaginably powerful. Now let us move to the second carrier of energy in a nuclear explosion, the high-energy gamma quanta released by fragment nuclei as they transition from excited to ground states. These photons also cannot travel very far. The overwhelming majority are scattered and absorbed by ordinary air within just a few hundred meters. But before being absorbed, they have time to cause many interesting effects. In particular, to generate an electromagnetic pulse capable of disabling electrical and electronic systems at distances of tens, hundreds, and sometimes even thousands of kilometers from the explosion site. When high-energy gamma quanta collide with the atoms of matter, for example, with nitrogen and oxygen in the air, they knock electrons out of those atoms. These electrons then travel in the same direction as the original gamma quanta, moving at speeds close to that of light. These electrons, like all rapidly moving charged particles, are affected by the Earth's magnetic field. The force acting on a charged particle in a magnetic field is described by the Lorentz formula. Inside the square brackets, there is a vector cross product of the particle's velocity and the magnetic field. This means that the force is always perpendicular to the direction of motion. And if a force is perpendicular to velocity, the particle's motion becomes circular or spiral. In our case, the electrons appear to spiral around the magnetic field lines while continuing to move forward along them. Spiral motion is a special case of accelerated motion, in the sense that during such motion, the magnitude of the velocity vector remains constant, but its direction changes. And as we discussed in one of our previous videos, any charged particle moving with acceleration emits electromagnetic radiation. This is exactly what happens to the electrons knocked out of atoms by the gamma quanta originating in the explosion's core. Because there are an enormous number of these electrons, and because they move at extremely high speeds, the resulting radiation is quite powerful. Its amplitude can reach up to 10,000 volts per meter, and its frequency is measured in millions of hertz. This radiation is what we call an electromagnetic pulse. Electromagnetic radiation is nothing more than a traveling disturbance of electric and magnetic fields. When such a disturbance passes through conductors and semiconductors, it induces chaotic parasitic currents within them, corresponding to voltages of hundreds, thousands, or even millions of volts. These currents are what act destructively on electrical and electronic systems, burning out electronic components, causing resistor breakdowns, capacitor explosions, and short circuits. That is why, in science fiction, and even in some popular science writing, one often encounters the claim that the electromagnetic pulse of a nuclear explosion would instantly burn out all electrical and electronic systems, plunging civilization back into the Middle Ages. In reality, however, while the effect of an electromagnetic pulse on modern infrastructure would indeed be destructive, it would not lead to such catastrophic consequences. First, electromagnetic fields are relatively easy to shield against. For example, if an electronic or electrical device is surrounded by a layer or even a mesh of conductive material, it can be protected from external influence. According to Lenz's law, the currents induced in that outer conductor generate electromagnetic fields directed opposite to the incoming field, effectively canceling its effect inside the protective shell. Therefore, any electrical or electronic device housed within a metal enclosure will be at least partially shielded from the electromagnetic pulse. Most cars, airplanes, and even personal computers that are not connected to the power grid at the moment of the explosion would likely survive it intact. Second, the strength of the electromagnetic pulse's effect on a given device depends greatly on the size of that device, more precisely on the length of its internal electrical circuits, within which parasitic currents will be induced. The strongest currents will arise in circuits whose lengths correspond to the wavelengths of the electromagnetic pulse, which are on the order of tens or hundreds of meters. Therefore, many modern gadgets, such as mobile phones, smartwatches, and similar compact electronics, will most likely survive the electromagnetic pulse. They are simply too small for electromagnetic fields to induce sufficiently strong currents within them. The systems most severely affected by an electromagnetic pulse will be electrical power networks. Within them, truly enormous voltages will be generated, burning out everything connected to the grid at the moment of the explosion. Even devices that are switched off will almost inevitably be destroyed. The electromagnetic pulse will also be extremely destructive to communication systems, especially television and radio towers, as well as mobile communication antennas, since these structures are literally designed to respond efficiently to electromagnetic radiation. So even if your mobile phone itself survives the electromagnetic pulse, you are unlikely to be able to call anyone with it for quite some time afterward. By the way, as for radio communication systems, those will most likely survive the explosion, provided they are not destroyed by other damaging factors. The reason is that radio networks were originally designed with nuclear war in mind, intended to serve as the main system of mass public warning in such an event. For that reason, a small battery-powered pocket radio could prove to be an extremely useful item after a nuclear explosion. It is worth adding that the effectiveness of an electromagnetic pulse increases dramatically with the altitude at which the bomb is detonated. Indeed, in the denser layers of the atmosphere, the electrons knocked out of atoms cannot travel very far, at best only a few tens of meters before colliding with another atom and losing their kinetic energy. Consequently, they emit radiation for only a short time and radiate relatively little energy. Therefore, the pulse's power is limited and quickly decreases with distance from the explosion center according to the inverse square law. If, however, the bomb is detonated higher, say, somewhere in the stratosphere or even in orbit, the situation becomes entirely different. In the rarefied layers of the upper atmosphere, high-energy electrons can travel for tens of kilometers, emitting electromagnetic radiation all along their path. Thus, while a surface or low-altitude nuclear explosion produces an electromagnetic pulse with a range of only a few tens of kilometers, a high-altitude explosion can affect an area thousands of kilometers across. For example, during the Starfish Prime test conducted by the United States in 1962, a nuclear bomb detonated in space at an altitude of about 400 kilometers above the Pacific Ocean disabled electrical systems in Hawaii, more than 1,400 kilometers away from the explosion site. It is rumored that both the United States and the Soviet Union worked on specialized nuclear warheads, so-called EMP bombs, designed to produce an electromagnetic pulse of greatly increased strength. Unfortunately, all information on these developments remains strictly classified, and all we know for certain is that, as of now, no nation officially possesses EMP bombs in active service. And now we come to the processes triggered by the main channel of energy release in a nuclear explosion: the heating of the bomb's material and the surrounding air through the kinetic energy acquired by the fission products. Within millionths of a second near the explosion's center, temperatures soar to tens or even hundreds of millions of degrees, hotter than the temperature inside the cores of stars. Under such conditions, matter does not merely evaporate. It turns into plasma, an ionized gas in which atomic nuclei float in a sea of free electrons. The pressure of plasma, like that of any gas, rises with temperature, and the pressure at the center of a nuclear explosion is enormous. It can exceed tens of millions of atmospheres. Because of this extreme pressure, the plasma begins to expand violently. In less than 1 millisecond after the start of the chain reaction in a bomb with a yield of 1 megaton, the plasma sphere expands to roughly 150 meters, and after 10 seconds, its diameter reaches about 2 kilometers. This colossal mass of incandescent plasma is called a fireball. Anything unfortunate enough to be within it is instantly destroyed, literally vaporized in a fraction of a second. However, as the fireball expands, its temperature rapidly drops, because all gases cool as they expand. When the fireball has expanded to about 150 meters, the plasma temperature falls to roughly 10,000 kelvins, and by the time it reaches about 2 kilometers in diameter, the temperature decreases to roughly 4,000 degrees. And we all know what any substance heated to such extreme temperatures does. It begins to glow. The intensity with which hot plasma emits electromagnetic radiation from each unit of its surface area is proportional to the fourth power of its temperature. This is the Stefan-Boltzmann law. And as we have just noted, the temperatures here are truly monstrous, especially during the first moments after detonation, so the energy radiated is enormous. For an observer careless enough to look at the fireball from a distance of 5 kilometers, it would appear 200 to 300 times brighter than the sun. During the entire explosion, a person standing 5 kilometers away would receive about 100,000 joules of electromagnetic radiation, equivalent to the kinetic energy of approximately 115 bullets fired from a Kalashnikov rifle. Of course, this energy is transferred to the human body and surrounding objects in a different way than bullet energy. Practically all of the electromagnetic energy is converted into heat in the surface it strikes. The nuclear sun of the fireball powerfully heats everything it illuminates, burning human skin and igniting flammable materials. Because of its extremely high temperature, the radiation spectrum of the fireball contains many high-energy short-wavelength components, including destructive ultraviolet radiation, the same type that causes sunburns, though in vastly greater amounts due to the much higher temperature. This radiation is extremely dangerous for the retina of the eye, so even looking at the fireball from a distance of 20 to 25 kilometers could cause retinal burns and permanent blindness. But that is not all that results from the formation of the fireball. It is also responsible for another, and perhaps the most destructive, damaging factor of a nuclear explosion, the blast wave. We have already said that when the bomb's material and the surrounding air are heated to monstrous temperatures at the moment of detonation, they begin to expand violently. However, this expansion does not take place in a vacuum. It occurs within the surrounding layer of ordinary, relatively cool air. The expansion speed of the fireball can exceed the speed of sound in air many times over, and under such conditions, the air cannot move out of the way quickly enough before the advancing surface of the fireball. Instead, the air in front of it becomes compressed and pushed outward from the explosion's center. At the outer boundary of the fireball, a layer of compressed air is formed, where the maximum pressure for the same 1 megaton bomb can reach about 75 atmospheres. As the fireball continues to expand, the pressure inside it begins to fall. This happens for two reasons. First, because of the expansion itself, since for a given temperature, the pressure of a gas is inversely proportional to the volume it occupies. And second, because the temperature also decreases, both due to expansion and due to radiative cooling, as the gas loses energy through the same electromagnetic radiation, the blinding flash of light we just discussed. By the time the fireball grows to roughly 2 kilometers in diameter, its internal pressure becomes equal to that in the compressed air layer around it. The expansion of the fireball then practically stops. It no longer supports from within the shell of compressed air. That shell, now freed from the internal pressure, begins to release the accumulated compression energy, transmitting it outward to the surrounding layers of air at normal atmospheric pressure. This creates a traveling wave of increased pressure, the shock wave, which moves outward from the explosion's center. Imagine this. At the moment it separates from the fireball, the air pressure at the wave front is about 75 atmospheres, or 7.6 million pascals. That means that every square meter of surface exposed to the wavefront experiences a force of about 7.5 million newtons. For a human being, The impact of such a wave would be equivalent to being struck by a full-speed locomotive. For buildings and structures, the situation is even worse. It is as if a locomotive were ramming every single square meter of their surface simultaneously. Fortunately, as the distance from the explosion increases, the strength of the blast wave drops rapidly. At a distance of 1 kilometer from the fireball's boundary, the pressure decreases to about 25 atmospheres. At 2 kilometers, to about 6 atmospheres. At 4 kilometers, to roughly 1.5 atmospheres, and so on. In open terrain, a pressure jump of about 1/2 atmosphere in the wavefront is considered lethal to humans. Such a pressure difference would occur at a distance of about 12 kilometers from the explosion's epicenter. At a distance of roughly 20 kilometers, the pressure difference would fall to about 1/10 of an atmosphere, no longer representing a serious threat. This marks the approximate outer limit of the shock wave's destructive radius. The blast wave of a nuclear explosion, in essence, is no different from the blast wave produced by an explosion of an equivalent amount of conventional explosive. The only difference is that it is physically impossible to pack, say, 1 million tons of TNT into a single bomb or missile, while a nuclear, or more precisely, a thermonuclear bomb with that same explosive yield can be created quite easily. This is the fundamental point of nuclear weapons. In principle, they are simply extremely powerful high-explosive devices, but with several additional damaging factors, such as the electromagnetic pulse, the light flash, and one more factor that we will now discuss: radioactive contamination of the area. The radioactive fallout from a nuclear explosion consists of 3 main components. First, there is the portion of the bomb's radioactive material that fails to undergo fission during the explosion. Even in the most efficient modern nuclear weapons, only about 30 to 40% of the fissile material actually splits during detonation. The rest evaporates and then disperses into the surrounding area as fine dust. Modern bombs generally use plutonium-239, an alpha emitter with a half-life of 24,000 years, which ensures long-term radioactive contamination of the affected area. Second, there are the fission products, the fragments into which atomic nuclei split during the chain reaction. These fragments themselves are highly radioactive. As a result of the explosion, and through their subsequent dispersal over the surrounding terrain, isotopes such as iodine-131, cesium-137, strontium-90, zirconium-95, and cerium-144 are formed, with half-lives ranging from several hours to several hundred years. Finally, to this radioactive mixture are added isotopes formed by the irradiation of the soil and air around the explosion center by the intense neutron flux produced during the chain reaction. These include silicon-31, aluminum-28, sodium-24, manganese-56, iron-59, and many others. To understand how all this radioactive material spreads across the terrain, we need to look at the final stages of the explosion, after the shock wave has detached and the fireball begins to fade. The air heated by the explosion's energy around the center of detonation begins to rise upward due to convection, carrying with it evaporated particles of the bomb and radioactive materials lifted from the Earth's surface. The convective air currents raise this mixture into the upper layers of the atmosphere, where the air pressure is lower. As it ascends, the air expands and cools, forming the characteristic cap of the mushroom-shaped radioactive cloud. Meanwhile, in the region from which the air has risen, an area of low pressure is created. Air from the surrounding regions rushes in to fill it, dragging along additional dust and debris, forming the stem of the mushroom cloud. This radioactive mixture of gases and fine dust, lifted high into the atmosphere, is then caught by the wind and carried away. When the rising convective flow weakens and the particles lose their upward momentum, the heavier dust begins to fall back to the ground, a process known as radioactive fallout. Fallout typically begins about 30 to 40 minutes after the explosion. A significant portion of the radioactive particles will settle around the explosion's epicenter, spreading over an area roughly 10 kilometers in radius. The rest will be carried away by the wind, forming a long radioactive trace downwind. For example, if the wind speed is about 10 kilometers per hour, The zone of lethal contamination will stretch for about 65 kilometers and be up to 15 kilometers wide. Within this area, radiation levels immediately after the explosion can reach around 10 grays per hour, approximately 1,000 roentgens per hour, meaning that a lethal dose of 5 grays could be received in just half an hour of exposure in open terrain. The zone of severe contamination, where radiation levels are about 1 gray per hour, would extend roughly 140 kilometers downwind, with a width of about 40 kilometers. Further beyond, in a region about 220 kilometers long and 75 kilometers wide, radiation levels 1 hour after the explosion would still be around 1/10 of a gray per hour, equivalent to about 1 Roentgen per hour. Even 1/10 of a gray per hour is a very high level of radiation. But there are, fortunately, two pieces of good news. First, these radiation levels are observed only during the initial period after the explosion, and then begin to fall rapidly, following what is known as the 7-10 rule. The intensity of radioactivity decreases tenfold for every time interval that is 7 times longer than the previous one. In other words, 7 hours after the explosion, the radiation level will be 10 times lower than it was 1 hour after the explosion. After 7 times 7, 49 hours, or about 2 days, it will be 100 times lower. After 7 times 14 days, or 2 weeks, it will be 1,000 times lower, and so on. In global radiological practice, radiation levels of about 1/100th of a gray per hour are generally considered not to pose a serious threat to life or health. In a 200-kilometer zone along the radioactive fallout path, radiation will fall to that level within about 7 hours. In a 150-kilometer zone, within about 2 days. And even the most heavily contaminated areas will become safe for short-term human presence in roughly 2 weeks. Second, shelters of almost any kind provide substantial protection from radiation. Even in an ordinary apartment, the radiation level will be about 5 times lower than outdoors. In the basement of a single-story house, levels will be 20 to 30 times lower. In the basement of a multi-story building, 100 to 200 times lower. And in an underground parking garage several floors deep, the threat can be reduced by a factor of 300 to 500. Thus, the real danger of receiving a hazardous radiation dose exists only for people located in the most heavily contaminated areas, within roughly 10 kilometers of the epicenter of a 1 megaton explosion, or directly along the central axis of the radioactive fallout path. Moreover, individuals within a 10-kilometer radius are likely to perish anyway if caught in the open, due to the other destructive factors of the explosion. In conclusion, if you have survived the previous damaging effects of a nuclear explosion, you have an excellent chance of surviving the radioactive contamination as well. Provided, of course, that you have not encountered a weapon specifically designed to maximize such contamination. The most well-known type of such weapon is the so-called Cobalt bomb. In this design, a certain amount of cobalt is deliberately added to the bomb's structure. Natural cobalt consists primarily of the isotope Cobalt-59. Under the intense neutron flux in the center of a nuclear explosion, Cobalt-59 captures neutrons and transforms into Cobalt-60, a highly dangerous radioactive isotope with a half-life of about 5.2 years. This half-life is short enough for the isotope to decay actively, becoming a powerful source of radiation, but long enough that it cannot simply be waited out in a shelter. By comparison, the typical radioactive mixture produced by an ordinary nuclear explosion decreases its activity tenfold within about 7 hours, whereas radioactive Cobalt-60 would require about 17 years to decrease its radioactivity by the same factor. Thus, cobalt is perfectly suited to render a given area hopelessly contaminated for many years, making it completely uninhabitable for humans. For this reason, cobalt bombs are often called the ultimate doomsday weapon. Fortunately, no country in the world has ever reported developing or, still less, deploying such nuclear devices. So this is the physics of a nuclear explosion, the most destructive natural phenomenon that humanity has learned to reproduce at will. In our upcoming videos, we will continue exploring the physical laws underlying the phenomena of the world around us, both those we observe every day and those we hope never to witness with our own eyes. If you enjoy the work we do on this channel, please consider supporting it here on YouTube or on Patreon and Boosty. The link to the latter, as well as the corresponding QR code, should now be appearing on your screens. Many thanks to everyone who already supports the project and to those who decide to join our community of physics enthusiasts today. That's all for now, dear friends. All the best to you, and see you soon in our next videos.